Hey, class, this is Mr. Heinrich, and I've got a nice backdrop of the Golden Gate Bridge because today we're learning about free fall. So if you were on the Golden Gate Bridge and you dropped a ball right off the top of the bridge, which is actually pretty tall, how fast will that ball be going every single second that passes? Well, we know intuitively that every single second that passes during the fall, it will speed up, but by how much? And of course, in this class, we're often neglecting air resistance because to add in air resistance or air drag or air friction, however you want to refer to it, would definitely affect the rate that the ball was falling. So let's get into that value right now. So when we say free fall, we're referring to a special condition for which the only force acting on the object is gravity. So let's start off with that statement. Free fall is a special condition for which the only force acting on the object, is gravity. Now, gravity is a force. It is one of the fundamental forces of nature. But we're not really ready to talk about force and talk about the equation for force and Newton's laws until next unit. So right now we're just looking at the effects of forces like gravity. So even in the last problems we've done, we've been talking about acceleration. Well, those accelerations are the result of forces. But again, next unit, we begin discussing forces. So what is the result of gravity on an object as it falls? Well, it undergoes a very specific acceleration. The acceleration due to gravity is negative 9.8 meters per second squared. And often we call this value little g. Just like we use little a for acceleration, when we use little g, we are referring to this specific value for acceleration. And you can see it's an acceleration. Its unit is meters per second squared. So let me get this pet peeve out of the way. One of my big pet peeves as a physics teacher is when people begin calling 9.8 gravity. 9.8 is not gravity. It is the acceleration that occurs because of gravity. Because gravity is a force, and forces are measured in newtons. Accelerations are measured in meters per second squared. Okay, enough on that. So if this is our falling acceleration, I want you to go ahead and picture, if you will, a scenario. So let's get into a scenario. Let's say you throw your cat upward. And you certainly can just use dots that represent the object. I'm going to try to draw some cats real quick. You throw a cat upward and it returns to you, because we're not going to hurt the cat. I like cats. I have a cat. His name is Milos. You know that. You watched the beginning course policies video. Let's see what happens to that cat velocity-wise, position-wise, and acceleration-wise as the cat goes up and comes back down. So let's draw a little cat in there. Make him a fat cat. Those are the best kind, right? Little feet. There he is. And that's his beginning position. Actually, you know what? I'm going to draw another one right down here. I'm going to draw one right here. So this is the beginning position for my kitty. And then we know that as he gets launched up with some velocity that we're going to identify in a second, that in the next moment, he's going to slow down because we know gravity is pulling downward on him as soon as we throw him upward. So maybe we represent this next cat picture with a slightly lesser velocity. So my question to you is now, in the next frame, and let's say that each of these frames is separated by a second, right? I'll say that. Each frame separated by 1 second, okay? In the next frame, where do I draw the cat? I should draw it even closer to this picture, right? So maybe the cat is right here, right? Put him right here. That looks good to me. Right? And in the next, oh, before I get to the next frame, what happens to its velocity? Well, it has decelerated. It is slowing down even more as it gets to that position. Then finally, let's put that kitty, that picture pretty much right on top of this picture. So it's going to be very, in fact, it might even overlap that picture slightly, right? That's okay. That's all right. Put them right here, overlapping that picture. And again, the faster way to do this is to draw these dots at the center of gravity or the center of mass. There's a slight difference between those two ideas, but we can use them interchangeably for now. Okay, so at his center of mass, I've got a dot representing that cat. And here, I'm not going to put a vector because his velocity is 0 meters per second. He's reached the top of his flight and he's about to fall back down, right? So let's go ahead and approximate this g value to -10 meters per second squared. Now, when we do calculations, unless the problem tells you otherwise, you're going to use -9.8. But when we're doing visualizations like this, it's a lot easier to use an approximation. And that's what we're going to do. And actually, for some FRQs that you get from the AP folks or on multiple choice questions, they like you to use this value because it keeps your answers nice and round, right? Okay. Let's say that we threw this cat up at 30 meters per second, which is actually a very fast throw. Throw that cat up. What speed does this cat have in the next second? Well, just look at our value of, let's write it over here, of -10 meters per second every second. That means that my velocity is changing by a -10 meters per second every single second. Is it really as simple as subtracting 10 meters per second off of that 30 meters per second? It's that easy. So the value of the cat's velocity in the next frame is 20 meters per second, right? What happens when you change this by -10? You get to 20. What happens when you change this 20 by a -10 meters per second in the next second? You get 10 meters per second, right? Which makes sense why I put a 0 up here, because in the next second, well, it's lost all of its positive velocity because of this negative acceleration. Okay, well, I'm not going to redraw all these cats for it falling back down because we know this cat's going to follow the same trajectory on the way down. So let's continue using our g value. What happens when you subtract 10 meters per second in the next second going downward from 0? Well, wouldn't you get a downward velocity of -10 meters per second, right? And what happens when you subtract 10 meters per second from -10? A negative minus something else becomes a bigger magnitude negative, right? So -10 minus 10 is, you are probably ahead of me on this already. It's a -20 meters per second, right? And then finally, sure enough, right as that cat returns to your hand, and you better be there, don't drop the kitty, right? I will call ASPCA on you. I think that's the organization, right? Okay, -30 meters per second. So what's interesting is this set of pictures could either be representing something falling up or something falling down. And the other reason I like to use this example is because typically when we think of free fall before we take physics, we think of something just falling straight down, right? But something can be in free fall and moving upward. Just rest assured that it's going to be falling down after some time because gravity is indeed trying to bring it back down to the earth, right? So free fall can be moving up or moving down. And that illustrates not gravity, but the acceleration due to gravity very well. Okay, so do all of our kinematic equations apply? Can I use V equals V naught plus AT? Yeah, I just have to plug in a negative 9.8 meters per second squared here, right? Also, be careful with your kinematics. If your velocity is downward, you have to use a negative velocity. If your displacement is downward, you have to use a negative displacement. Your time will never be negative because time has to be positive. Remember, negative time means time travel. We can't do that. So it doesn't matter what kinematic equation I decide to use. In fact, most of the time when I write the second kinematic equation, I start writing it as delta y because I know I'm moving in the y-axis, right? If you put delta x here, it's not the end of the world. So I'll put v naught plus 1/2 AT squared. And you might be saying, well, why aren't you putting G there? Well, if you do put G here, you have to be careful because you know inputting a G here generically makes this what? Makes this plus a minus because that G has a negative value. So if you're going to put G here, don't forget to change that to a minus. So honestly, I know I don't usually do that because if you input a minus and then you plug in a negative 9.8 later and then you turn that back into a plus, you're in trouble. I hope that makes sense to you. Delta y, right? And the last one, of course, would be delta y equals v plus v naught divided by 2 all times t. And all these velocities are happening in the y-axis. When we get to projectile motion, and we're dealing with 2 dimensions at the same time, we will have to start putting that little y subscript if we're talking about the y-axis, or the little x subscript if we're talking about the x-axis for our velocity. But that's next chapter, in chapter 3. All right, let's get to an example problem to illustrate which equation to use and how to apply free fall. Okay, let's say you're in the dorms, you're up to no good, you're throwing water balloons at people that are sleeping or taking a nap on the lawn below you, right? I think this is a good idea. Certainly, they won't mind, right? We're in college. Everyone knows in college that there's a fair amount of antics that take place. Because, man, you got to let loose after all that studying. So there's someone just resting innocently on the lawn below you, and there's your dorm window. Some old building built in the 60s or 70s, right? That's all made of cement. That's the kind of dorm I lived in. And since then, they built beautiful dorms, which didn't benefit me. I lived in this cement bunker of a dorm, and then I lived in this old red brick one the next year. And at Cal Poly, that's where I went. Now they have these awesome ones where it looks better than most apartments that people live in. Okay, enough of that. This guy throws the balloon downward, and let's say the person throws the balloon downward with a pretty fast speed, maybe 15 meters per second. And let's put some verbiage to this, some text to this. We'll say a student throws a water balloon downward let's see, do I want to give you that velocity? Yeah, downward at 15 meters per second. Yeah, I already did give it to you, right? Downward at 15 meters per second, period. If it takes, I'm going to say this, if the window is, what would be reasonable, maybe it's really high up there, 4 meters above the ground. If the window is 4 meters above the ground, what is we're going to ask two questions. The time it takes to strike the napper and B, the velocity the balloon, let's talk like proper English students, the velocity with which the balloon hits the napper. Okay. I think that we've got everything we need now. And with free fall problems, sometimes you feel like you don't have enough given, but remember, you always have a given right off the bat. Your first given that's always known, if gravity is the only force acting, and it is, your first given would be your acceleration. Your acceleration is in fact g. You don't have to write g if you don't want to, which is negative 9.8 meters per second squared. Right? That's always known. Now, when I was first taking physics, when I thought about this, I'm like, that's the only force acting? I mean, this guy just threw the balloon down, right? Didn't the throw, wasn't that some force right there? So gravity's not the only force acting. The problem is talking about the time interval for which the balloon has left the person's hand and is now traveling towards this person's face. So that's the time period we're concerned with. And in that time period, the balloon it's already been accelerated by the person, right? It's no longer touching their hand, and it hasn't struck the person's face yet. So it's a very specific time period when it's left the hand before it hits the face. So gravity is the only force acting. That is our acceleration. On to the next quantity. I'm going to go ahead and write my next set of quantities here. I'm going to see if you agree with everything I've written. How about that? Do you agree with my set of givens, and we're looking for time in part A, and in part B, we're looking for final velocity, right? I hope you don't agree with my givens, because there's a slight error for the initial velocity and for the displacement. He's throwing it down, and down typically, or by convention, is considered to be negative, right? Also, this balloon is displacing downward, not upward. So it's changing its position in the downward direction, and therefore the delta y is also negative. Now, as you get more comfortable with physics, could we call the downward direction positive? We could. We have that right and ability as the problem solver to call down positive and up negative. Why would I want to call down positive? Because then I could say that each one of these values, which are all directed downward, by the way, these are all vector quantities, they're all directed downward. I could call them all positive, which would make plugging in numbers a little more convenient, right? A little less cumbersome, right? But let's not break convention. Let's keep going with our downward convention as being negative. Let's find our time. Our time can be found by using which kinematic equation? Well, we're not dealing with the final velocity yet, so that looks like the second kinematic, right? So I'm going to write here delta y equals v naught t plus 1/2 at squared. And I'm going to realize, oh no, I can't cross anything out, right? I have to populate this with a -4, this with a -15, this with a -9.8, which when multiplied by 1/2 is -4.9, and you'll have a quadratic formula on your hands. And you certainly can do that. But how about we sidestep that quadratic formula and do part B first? Let's do part B first. There's nothing wrong with that. A lot of times you can do that in physics problems. But a lot of times they build on themselves and you can't. So you just have to kind of decide if you're able to. So now let's forget about time for a second. Do we have an equation that uses all four of those? We do. It's v squared equals v naught y. Oop, look at me slipping in the y. There's nothing wrong with that. I could put vy and v naught y. I could do that, but let's not add extra subscripts until we absolutely have to, right? Plus 2a delta y. Now, that's a squared right there. Don't miss that squared. We've got to find final velocity, and this thing is already set up. Now, I'm going to square root both sides in order to isolate this v. And I want to remind you about something very important in algebra. When you square root both sides, there's two correct solutions. Mathematically, there's two correct solutions. Physically, in this physical scenario, there's only one right solution. But technically, you're supposed to put a plus minus in front of that square root. Now let's use our common sense. This balloon, right before it hits this person's face, right before it gets there, has an even faster negative final velocity that we're looking for. Hasn't hit him yet, but it's about to. So we know the answer is a downward velocity vector. Therefore, we should accept the negative answer, not the positive answer. Okay. So let's plug in our numbers. Negative square root, what we got here? Negative 15 meters per second squared plus 2 times negative 9.8 meters per second squared times negative 4 meters. I fit it. Perfect. And you can see here we're going to have a negative times a negative and end up with a positive, right? So this whole thing or term will be positive, and we'll square this negative, and that will also be positive. There's no danger of us getting a negative in our root. And if you get a negative in your root, something has gone wrong. It's probably with your assigning of negatives in the givens. That's also a way to problem solve or check your problem solving as you go. You should not have negatives in that root. Okay, square root. You do the calculation, I'll do it too. I got 17.4. I got 17.4, but remember we have to say it's the negative 17.4 meters per second. And now that we have that answer, we're going to pick an equation for finding time. Now we can avoid the quadratic because we have a new given, as long as we didn't mess up, right? Which is actually why I'm double checking this right now, just to make sure. I want to make sure we don't carry forward bad information. It is, in fact, 17.4. I'm going to go to my easiest equation, and the easiest equation of all the kinematics is by far the first one. Right? It's definitely this one right here. Because there's no squareds, it's pretty easy to maneuver different variables around and isolate. Let's isolate time. It would be v minus v naught divided by a. If you go through the steps, you would subtract v naught and then multiply both sides by a. Let's plug in our values. We'd have a negative 17.4. And remember, this is time we're talking about. We cannot end up with a negative answer. So let's see if everything plays out correctly. Minus your v naught, when your v naught was a negative 15 meters per second. Right, right. And then we have divided by a, which is negative 9.8 meters per second squared. Well, we have 17.4 negative plus 15, right? This turns out to be plus. So, oh no, we have a negative in the numerator, but that's okay. We have a negative in the denominator. The negatives divide out, and we end up with a positive answer. So this thing is not going to spend much time in the air. I'm sure the person on the ground is very happy about that, right? And I end up getting a time. This is typical for these types of problems because things don't spend a lot of time in the air if just people are throwing them, right? If we have cannons shooting things or guns shooting things, then yeah, they can spend a lot of time in the air. We have 0.24 seconds. So to travel those 4 meters, it only took basically a quarter of a second. So that person would really have to be aware that the throw is happening to even think about getting out of the way in time, right? Well, there's certainly harder problems in this one, but it illustrated a lot of important concepts, identifying your negatives correctly, sometimes doing a part B before a part A, that's okay to do, and showing us that an object that's in free fall, where gravity is the only force acting, it will accelerate at a rate of negative 9.8 meters per second each second. Thank you. Have a good day.